was fun, like the last.
Did anybody check out the homework and find they had questions? Yes.
It was on the last problem, like it was like with the like weird like kind of like picture like that, you know?
Do you know what section it was on?
It was like on section 4.1. I had a question on that as well because like it was like my friend helped me with it. He's not even in this math, but he's in a higher math than I am.
Which problem was it?
Oh, that's nice. Like I got the work.
Was it the one with the railroad?
Oh yeah, that one.
Okay. So this isn't actually due for a while, so if you haven't looked at this yet, that's okay. This is a train track. So the train tracks are made of metal. Consequently, they expand when it's warm and shrink when it's cold. When riding in a train, you hear the clickety-clack of the wheels going over small gaps left in the tracks to allow for this expansion. Suppose you were a beginner at laying railroad tracks and forgot to put in the gaps. Instead, you made a track 1 mile long that was firmly fixed at each end. On a hot day, suppose the track expanded by 4 feet. So yours is going to be different. Mine is 4 feet, okay? And therefore buckled up in the middle, creating a triangle. So you have a 1 mile track and you don't leave the expansion joints, so when it gets hot, there's no place for that metal to expand. Sometimes you see this on siding on houses. If you see siding buckled, it's a lot of times because someone who didn't know what they were doing fastened the siding on firmly, and then the hot sun comes out and the siding expands and there's no place for it to go. So happily we do not see this on train tracks. But let's go ahead and draw a picture of this and see what happens if we did see this with train tracks. So I'm going to write this down and then switch to the document camera. So this is 4.1, Mindscape 15, and there's 1 mile of track, but now it's buckled up in the middle because it's expanded, and there's now 1 mile and 4 feet between this. So overall this expanded 4 feet, so there's 2 feet more on each side here. So half of it on each side. So we need to get some dimensions here and change over from miles to feet, and then we can go ahead and look at a right triangle, because this little piece is a right triangle. Does anybody know how many miles, how many feet are in a mile? Yeah.
5,280.
Good job. 5,280. So I have half of that, actually, don't I? Because I have half on each side of the peak. So 5,280 divided by 2, that's 2,640 feet. So that's the half mile. And then we're trying to find this x, how much did it pop up? And up here there's 2 feet more than a half mile because of the expansion. Okay, so you're not going to have 2 feet probably. Some of you will. Okay, some of you will have different amounts. So we use the Pythagorean theorem here. Make sure the hypotenuse is the 2,642 because the right angle is formed by the height x and the bottom of the triangle. So we have x squared plus 2,640 squared equals 2,642 squared. So let's see what these numbers are. 2,640 squared. $6,969,600. 2,642 squared. $6,980,164, and then we'll subtract 6,969,600 from both sides. We get 10,564. So we'll take the square root of both sides and get our answer. $102.78 feet. That's a lot of popping up. This has all happened right in the middle. Anybody have any questions? It's very surprising to me. It seems like if it only expands 2 feet here and 2 feet here, that it should be something like less than 2 feet, but instead it's 102.78 feet. I find that very interesting. Okay, let's go on with today's work. We've been looking at the Pythagorean theorem. Now, when the Pythagoreans learned a squared plus b squared equals c squared, they almost certainly would have been thinking about squares. So a square that has sides a for length will be an area of a squared, and a square that has sides b for length will be an area b squared. A square that has side c for length will be an area c squared. So the Pythagoreans gave us geometry before we had algebra. In fact, the whole world worked on geometry before we had algebra. So they would not have thought of this in terms of letters. They would have thought of this in areas. So they would have pictured a right triangle with a square C by C, okay, C by C, and another square A by A, and a square B by B, and they would have physically noticed that if you took these squares and squished them up and cut them up into little pieces as necessary, you could fit them into this big C squared exactly. So that's how the Pythagorean theorem would have come to us. It would have come through geometry. Mathematicians noting that you could take these pieces that were perfect squares, lengths A and B for sides, disassemble them as you need to and fit them in to C squared. So that's what we're going to be doing today. We're going to be looking at proofs of the Pythagorean theorem. The life lesson in this section is to experience ideas in as many ways as possible. So we're going to look at the Pythagorean theorem proof in 3 different ways, hoping that one of them makes sense to you. Okay, so you have 3 different ways to pick from. We're not even going to look at all the ways that the Pythagorean theorem's been proved. It's been proved in many different ways. Does anybody know a president of the United States who did mathematics and has his own proof for the Pythagorean theorem? That's probably something only mathematicians care about. That'd be James Garfield. So James Garfield has his own published proof for the Pythagorean theorem. How about an artist, a famous artist who would go home from a hard day at art and relax by doing mathematics and has his own proof for the Pythagorean theorem? There I've giving you half the answer because it's a man, because I said his own proof. So, anybody have any ideas on who that artist could be? Do we have any art majors? It'd be Leonardo da Vinci. Okay. That makes sense now. Yeah, if you know a little bit about him, that makes sense. Well, we're going to take our shapes, so hopefully you cut yours out. Does anybody need the scissors? It's floating around here somewhere. Anybody need the scissors? Okay, can you please pass those down? So you can label the parts on your triangle so that we all match, okay? And so we're all talking about the same. The hypotenuse you can label C. And then make the long side A and the short side B on your right triangles. So short side B, long side A, and then we'll all match. You'll see it better on the yellow one. And C will be the hypotenuse. Now don't do any other writing on your templates, because if you want to bring them to the quiz, then you can, but not if they have writing on them. But you can certainly label the A, B, and the C. So A for the long side, B for the short side, C for the hypotenuse.
Why does B have to be the short side?
It doesn't. A and B could be interchanged, so I'm only saying this so that we all match, so that when we're talking, things make sense. So A and B could be interchanged, but C should be the hypotenuse. And I shouldn't call A the long side either. A is the long leg. C is the longest side. Yes?
Does only one have to be?
You can label all of them, and then they'll help you as you're trying to figure out what you're doing.
Because they said one for the quiz, say one for the quiz, so.
I'm just saying, don't put a bunch of other writing on there, on the triangle, just the A, B's, and C's.
Yeah.
Now, did anybody find the relationship between A, B, and C in this square? What this extra square was? Anybody figure out what length that is? Well, you can fool around with your shapes and see if you figure it out. In the meantime, we'll go ahead and just work on finding a square C by C, okay? So we have C by C. So let's build a square that's C by C. I'm going to build the square inside. Let's put a piece of graph paper down so you don't have this writing in the background. If you have graph paper today, your work will be a little easier. If you don't have graph paper, if you have a straight edge, that's almost as good. So let's build a square inside our triangles that's C by C. Okay, so you can know this is a square and not a parallelogram, because these two small angles on the right triangle add to 90 degrees. So on a right triangle, this angle is 90 degrees. And what do all the angles on the triangle add up to?
360?
Not 180. So you take 90 away here, and that means these two add up to 90. So you have 90 here and here. And then the whole straight line, how many degrees are in a straight line?
180.
Good, 180. So you have the 180 minus the 90 is 90. So these are all square corners. We have 180 minus 90. We have square corners. So I'm just establishing you for this, that this is a square. It's not a parallelogram. All right, now let's transfer this as a drawing to our paper. So if you can fit it on your paper while you're drawing, then you can look at it, or if you can sit it on the desk next to you. I'm going to see if I can. Oh, it's as small as the screen goes. That's as small as the screen goes. So I'm going to just set this on the side and copy it down. So this will be proof 1. So as I said, we're going to do 3 proofs. Hopefully one of them will click for you. Proof 1. So I'm going to make so I'm going to make a a right triangle that's 3 by 5, and another right triangle butted up to it that's 3 by 5, so that's 8 squares. So if you don't have graph paper, you could make 8 lines, okay, 8 lines tall, and if you had a ruler, you could make it 8 the same width. So 1 to 2, okay.
So like there are 8 squares by.
Yep, I'm making a square 8 by 8 because ours were 3 inches by 5 inches, and it's pretty easy then to copy that down.
Okay.
So I made the square 8 by 8, and then here's 3 by 5 right here. So A was the longer leg and B the shorter leg. Now we don't label these 3 by 5, right? Because this has to be true for any right triangle to be approved. So that's why we're saying A and B and not 3 and 5. This has to be true for any right triangle, not just one with legs 3 and 5. Now as you draw these for a proof, it's not enough to draw the picture. You have to have the letters on to identify that the sides that are the longer legs are all A, and the sides that are the shorter legs are all B. That's because we're trying to prove something. And in our proof, we have to have identified what parts are the same. You would identify that these are right triangles. And now we can have a C, so here's C squared. That's what we had made. We made a square that had length C. Okay, so make sure you have your letters on, long legs A, short legs B, and then you have C squared. Okay, well we're gonna now use our same 4 triangles to make another shape. Make sure you're all caught up on that shape. Now we're going to make a shape that's A squared and B squared. Okay, so we're going to use the same 4 right triangles to make A squared and a B squared. So let's zoom out here. So we're going to make our cards back into the 3 by 5 shape. Where in this screen do you see a A squared square now? Where is there a squared? A square that's A on one side and A on the other. On all 4 sides.
The upright.
Yeah, right here, right in here. So this is A across and A down. So this is a square A by A. I didn't outline it over here, but this is A by A. Okay. And where is there a square that's B by B? Upper left. Okay, so that's B by B. So let's transfer this drawing onto the paper 2. I don't think it, maybe this will fit. I don't know. So I'm going to make it, so 5, it'll be 8 units tall again, won't it? No, let's see. We go 5 plus 3. Yeah, 8 units tall.
And this will be A, but
Yeah.
A squared by A squared.
Well, let's see. We're going to draw another square, 8 by 8. Okay, if you only have lined paper, you'd make it 8 lines tall. Okay, so looking at my picture, I had basically a 3x5 card on the upper right. Okay, so I have a 3x5 card in the upper right. That's cut on the diagonal. And I had a 3x5 card in the lower left. Also cut on the diagonal. So you have to be able to just, to draw these, not just create the figures, because on a quiz you can't hand in your figures, right? So you need to be able to get the drawings down. So we label the A for the long legs again, and the B for the short legs. And these are right triangles. And actually we don't really care about C this time, but you could put C if you want. So the A, B, and C in this picture are also identifying that you're using the same triangles as you were on the picture on the left. But now you have a square, A by A squared. And you have a square B by B, which is B squared. So you have your right corners labeled, you have your A's on your long legs, you have your B's on your short legs, C on the hypotenuse. Now, we know that these are the same size because we just sketched them 8 squares. But again, these A's and B's are supposed to stand for any lengths, not 3 and 5, but any lengths A and any lengths B. So to show that these are the same size, we look at the big square. How big is this big square? What is the length across the bottom? So a little bit more than A plus B. Yeah, A plus B. So all the way across is A plus B. And the height is A plus B. So the square on the left is A plus B across the bottom and A plus B tall. So its area is A plus B times A plus B. That's how you find the area of a square or a rectangle, length times height. And it's equal to this one, oops, because this, I didn't label the A here because it was not on a triangle, but the A's up here. A plus B across. And the height, you can have the A plus B tall. So both areas are the same, even if we had drawn them the same. The A plus B's would identify that we are using the same 4 triangles, and the A plus B on the one triangle is the same length as the A plus B on the other. So how does this prove that A squared plus B squared equals C squared, or how does it lead us to that conclusion? Well, they're equal. Okay, you can write that they're equal. These are equal areas. Equal areas. So how is this going to lead us to the conclusion that A squared plus B squared equals C squared? Well, let's look at what we have over here. On the left side, you have C squared plus 4 right triangles. what do you, I said the right side, I'm sorry, that's the left side. What do you have on the right side? So your whole area is made up of what? It's made up of the a squared and the b squared and the 4 right triangles. Those 4 right triangles are the same. That's why they're labeled, so that we can point out that they're the exact same right triangles. So this is, does anybody know the area of a triangle formula?
Isn't it half times base times height?
Yes, 1/2 times base times height. So you have 1/2 times b times a. And over here you have a squared plus b squared plus 4 times 1/2 times b plus a. I'm sorry, b times a, not b plus a. So, in other words, you can take away from both sides the same thing. You can take away from both sides those 4 right triangles, and what you have remaining is the area c squared equals a squared plus b squared. So the initial areas are the same. They're both length AB, but a plus b times height a plus b. But if you take this area and remove the 4 triangles, since they're the same on each of the 2 figures, if you remove those 4 triangles that are the same on both figures, what you have left is still the same. So you have the c squared equals a squared plus b squared. So that is your first proof. Does anybody have any questions on it? You need the drawings, you need the labels, you need a little bit of algebra to say what you're doing, that you started with the same areas and you take away the 4 right triangles, and since the area is composed of c squared plus the 4 triangles over here and a squared plus b squared and the 4 triangles over there, when you take away the same amount from both, you're left with the same amounts. C squared equals a squared plus b squared. Okay, well, we'll go ahead and look at another proof. Before we do that, I wanted to demonstrate that you can make any proportion right triangles for this. Has anybody figured out yet how this square is related to the a and the b?
It creates 2 other triangles in it.
It does, doesn't it? If you put it on there, it does create 2 other triangles. Well, it has a little bit of peek out of it, though. If you take your A and your B like that, the square is that size. So the length of each side on the square is length A minus length B. The long leg's length minus the short leg's length. So you could put that on your square too, A minus B on the side there. Okay, so we have particularly shaped right triangles, but these proofs are true for any right triangles. So here I made some more right triangles that are not 3 by 5. So you can see that you can make the same proof with triangles that are not 3 by 5. This is big enough to show? Okay. So the proof would come out the same because, again, we're not using that the triangles we made are 3 by 5. We're using that the long side is A, the short side is B. We get a big square that's A plus B for length, not 8. This is true for any size right triangles, as long as you are careful and you cut them out. And on my cutouts, I have another square then that's length A minus B that I could work with. Well, let's take a look at proof 2. For proof 2, we're going to need a square that's C big on the outside. So this time we need a square that's C big on the outside. So we did C, a square that was C big on the inside before. Can you rearrange your triangles and make a square that's C on the outside? So go ahead and experiment with those. And I'll walk around and see how you're doing. You're looking for a square C by C, but this time on the outside, not the inside. Where the scissors end up? Can I please have them? Thank you. Hey, I see one. Yay. I see someone got it. Okay, I see someone had it, so I will show you. So you're looking to get the C's on the outside. So if you put your C's on the outside, you again make a square, C by C. And you know that these corners are 90 degrees. You didn't make a parallelogram because the two little angles in a triangle add up to be 90 degrees in a right triangle. So this little angle and this little angle add up to 90 degrees. Now you actually have a square in the middle as well because these are 90 degrees since they're right angles. Did anybody notice what size that square is? Yeah, that's right, the size of your square. Right. So it's the size of your square. So this is the drawing that we have to get transferred on the paper. See how you have the two legs of the right triangles together here? You have the long leg A minus the short leg B. So you have length A minus B in here on the square. Let's see if I can put this up top and draw the picture down below. This one I'm not going to try and draw to scale because it's just too, this was like 5.83. I guess I'll draw 8 by 8 again, but it's not going to be to scale. So if you don't have a ruler, please use a small piece of paper to be your ruler. So if you don't have a ruler, you can take the lined paper, another piece of lined paper, and make 8 lines this direction just by turning it sideways. And your lined paper can be your ruler. You're just measuring in line number, how many lines instead of in centimeters. Okay, so getting these triangles on is a little tricky. What I recommend, if you don't have a ruler, take out your ID. Your ID makes a nice straight edge, okay? Or perhaps one of your triangles would work. So I suppose you could pick up one of your triangles, since you can look at mine on the screen. Take one of your triangles like this and use it to draw with. I'm going to use a ruler, but you could use one of your corners. Okay. So either your ID or one of your triangles. And you want to put that in each corner. Once you have one set down, the others will follow along that edge. So just pick up one of your triangles to use in the corner, or your straight edge. Oops. Gotta watch those curvy ends on your rulers. There. Okay, so you can use a ruler or one of your triangles. You're gonna get that in there. Okay. So we do need all of these parts labeled. So once you have the triangles sketched in, go ahead and make sure they're right triangles. Because they're right triangles, that's going to make that shape into a square because of those two little angles adding up to be 90 degrees. So long leg was A, so label your long legs A, and your short leg was B, so we'll label that B, and then the hypotenuse is C. You also need that this is a square on the inside, and it is a square, again, because we're using right triangles, that forms a square on the inside. And you need the length of the square inside, the length of the sides. So that was the A minus B for length in here, A minus B. Now, proof 2 has more algebra. So for those of you who like more algebra and less drawing, this one has more algebra and less drawing. So this is a square that's C by C. It's C squared. And it's formed by taking these four right triangles and the square inside. It's formed by taking those four right triangles and the one square. So now we're just going to write out the areas of the four right triangles and the one square. So the four right triangles each have an area 1/2 times base times height. In ours, that's 1/2 times b times a. And the square has an area a minus b for one side and a minus b for the other. So a minus b times a minus b for length times height. So we have c squared, and this part's not too bad. The 4 times a half, that's the same as 4 divided by 2, that's 2. So you have 2ab there. Right here, do you remember how to do FOIL? Okay, if you don't, this might not be your favorite proof. Okay, we're using FOIL. It stands for what? Who remembers what does FOIL stand for?
First, outside, inside, last.
Good. First, outside, inside, last. So first means you multiply the a times the a. So the a times the a is the a squared. Outside, well, for outside means you multiply the a times the negative b. So the a times the negative b, that would be a negative. A positive times the negative is negative. So negative ab. And the inside is negative b times positive a, so that makes a negative. Another negative ab. And the last means the negative b times the negative b, and the negative times the negative is positive, so that would be positive. Positive b squared. So on this is an aside. I'm just reminding you to use FOIL. That wouldn't have to appear in the proof. I'm just reminding you. So if you're wondering where that came from in your notes, you have it. And now this is a positive 2ab, and you're subtracting away one ab, and then you're subtracting away another ab. So all the ab's cancel each other out. You have 2 positives and 2 negatives, they're gone. So you have c squared equals a squared plus b squared. So if you're a more algebraic person, you might like this proof best. There's less drawing, more algebra. Anybody have any questions on that? So everybody needs to learn one of these proofs so that they can present it on a quiz. And again, the things that are worth more points, one of these proofs would be one of the things that are worth more points on a quiz. Well, let's take a look at the third quiz, the third proof. The third proof has the least algebra of all. And to do it, we need to rearrange our shapes again. Before we do that, though, let's copy down this shape again. Okay, so we're going to look at proof 3. And proof 3 has 2 drawings. One of the drawings is the shape, so let's copy that again. Where's another piece of graph paper? I know I had graph paper. Where did I put it? There it is. So this is good practice if you liked proof 2. You get to draw this figure again. So we'll make it 8 by 8 again just because that's what we've been doing. So this proof is going to be all geometry. No algebra to write out. Just the tiniest little bit. Mostly labeling. Okay, so we have a square. And remember how you finished sketching in the corners. We took this shape here and helped it along because we're trying to draw this shape, okay? So you take your triangle, or I'm going to use a ruler because otherwise I get sketch marks on my triangles. And I have to use mine over and over again, so I don't want sketch marks. So once you have one established, then follow the marker line that you drew, or the pen line, to make your next triangle. This takes some practice. Okay, so if yours are coming out kind of wonky looking, just practice a little bit. Don't forget, you don't just need the drawing, you need the labels on the drawing. So long legs, A, short legs, B. So these could be any right triangles. Put little corners on to make sure they are right triangles. So this could be any right triangles, and then in the middle you have that B minus A square. Square B minus A. Oh, you're right. Good job. Thank you. A minus B. A minus B. Okay, so the big thing here is that you used all of these shapes to make C squared. All of these shapes together made C squared. That's what the big deal is here. So what I'd like you to do is to use all of those shapes to get A squared and B squared together. So A squared and B squared together. So keep working on them, fiddle around. I'll come around and see how you're doing. You're looking for a square A squared and a square B squared using all of your shapes at once. Because if you can use all of these shapes to make C squared, and you use the same shapes to make A squared and B squared, well then you have shown A squared and B squared equals C squared. So fiddle around with these. So this time we won't want any empty space because there was no empty space in that C squared. You like puzzles? What you got? You have C squared, right? Let me see. You have A. Oh, so you have some extra. So you do have a square A squared, but you got a little extra in there because this got used twice. This got used twice, and this is it. So you did make a square A squared, but you got a little peak one. Some was used twice. So we don't want to have any empty space because we didn't have any empty space when we used our shapes before. And we don't want any covered up because we didn't have any covered up before. It has to do with your assignment today. What is your class activity? Yeah.
Is the penalties?
Nope. So you needed those. Did anybody look? It says to show your fat L. Yes, make a fat L shape.
Oh my God.
So that gives you a little hint. I don't think I like the way your mind is working.
My mind is not working today. Actually, this one is your C. This is your side opposite.
Oh my god, yes. You just killed me right now. I'll take your off.
Hey, you got it. Good job. You have it. Yeah, you have it.
There.
Now you have to think about why it's a squared plus b squared. One person got it. Okay, I'm going to leave you to think about that over the weekend, and we're going to put it together on Monday since we only have 3 minutes and we'll have to write it down, and I want you to think about it. Hey, you almost have it too. So some of you have it and some of you almost have it. So see, now you have it. See, yeah, now see, pardon? That once you get the fat L, you will have the class activity. So if you want, you can wait till Monday, and we'll do it together. And hopefully you can figure out what it means too, because the class activity asks you, well, what is that showing? Yeah, you have it too. Lots of people getting it. That's great. We'll actually put it on paper on Monday. I'll see you then. Have a good weekend. Aren't you glad this isn't snow, by the way?
If it starts snowing now, I will cry my eyes out.